Welcome to this explainer. Today we're unpacking the absolute fundamental building block of internet security. I'm talking about Open SSL. You know, whether you're a seasoned developer, a system admin, or just starting to dip your toes into cybersecurity, understanding Open SSL is pretty much non-negotiable. It's literally the silent engine keeping the internet secrets safe. So in this explainer, we're going to completely demystify how it works, how it's structured, and exactly how you can build it from scratch. Okay, let's dive right in.
Think about it. If you interact with the internet at all, you are interacting with Open SSL. It's the indispensable utility operating behind the scenes of almost every major web server out there. It honestly doesn't matter if your infrastructure is running on Apache, Nginx, or Tomcat. Open SSL is that trusted, built-in mechanism securing those communications. It really is the gold standard.
So why the massive adoption? Well, it really comes down to its core capabilities. You can use it for your basic day-to-day tasks like encrypting a confidential file, securely signing documents, or generating a cryptographic hash. But it scales all the way up to the heavy lifting, setting up full TLS or HTTPS for a web server, and generating the necessary secure key pairs and certificates. It even provides a robust API. So if you're writing your own custom security software in C, you can just leverage OpenSSL's functions instead of reinventing the wheel. It's just an incredibly versatile toolkit.
Here's a quick look at our roadmap for today. First, the Universal Crypto Utility. Then, versioning and core libraries, followed by the power of engines. After that, we'll get into the practical stuff, building OpenSSL on Linux, and finally, building OpenSSL on Windows. All right, starting with Section 1, the Universal Crypto Utility, the open source standard for cryptography. The real secret sauce behind its massive adoption? It's the open source advantage. Because the core library is written entirely in C and licensed as open source, it's completely free to download for both commercial and non-commercial use. You've got the total freedom to modify the source code, build your own custom solutions, and then distribute that modified software freely. That level of accessibility is exactly why you'll find OpenSSL pre-installed by default on almost every single Unix and Linux distribution out there.
Moving right along to Section 2. Versioning and core libraries. Understanding the architecture.
Now this is super important if you're managing systems, because OpenSSL recently underwent a pretty massive shift in how it structures updates. Under the old versioning scheme, think version 1.1.1, a letter at the very end indicated a bug fix or security patch. If you upgraded that letter, you were good. It was safely backwards compatible. But starting with version 3.0, they moved to a new scheme using a patch digit instead of a letter. Keep in mind, in both schemes, changing the major release number is absolutely not backwards compatible. A major upgrade means you really need to test your applications to make sure nothing breaks.
Under the hood, it's basically a strict three-tier hierarchy. Right at the top, you have the Open SSL utility. That's the command line tool you and I actually interact with. Beneath that is libSSL, which handles all the specific SSL and TLS protocols. But here's the kicker. libSSL doesn't actually do the math itself. Nope, it relies entirely on the foundational library sitting at the bottom, libcrypto. Libcrypto is the true powerhouse here, performing the actual cryptographic operations, the encryption, the signing, the hashing, and the key agreements.
Section 3, the power of engines, accelerating cryptography. Software is great, right? But it definitely has its limits. Maybe your CPU is just too slow for bulk operations, or maybe you want to keep your private keys physically isolated from the main system. This is exactly where OpenSSL engines come into play. Think of an engine like a highly connected property dealer. Sure, you could sell your house entirely on your own, just like OpenSSL can do all the crypto math and software, but a property dealer has the specialized contacts and tools to do it much faster and way more securely. Similarly, engines are libraries that allow OpenSSL to offload that heavy lifting to specialized external hardware, like a hardware security module. It massively accelerates the process and locks down your keys. All right, let's get hands-on. Section 4, building OpenSSL on Linux, from source code to installation. You might be wondering, if it's already pre-installed on Linux, why do we need to build it? Well, you've probably been there. You try to run a simple update command, like apt-get upgrade, and your Linux system tells you, often to your total frustration, that OpenSSL is already at the newest version. But then you check the OpenSSL website and see a much newer release exists. This happens because Linux distributions intentionally hold back OpenSSL updates, Many critical system programs depend on a specific, stable version. Upgrading it system-wide could literally break those apps. So to get the absolute newest features for your own projects, you actually have to download the source tarball and build it yourself. So how do we do that? The standard Linux build sequence is surprisingly straightforward. First, you pull down the source tarball from the Open SSL website using wget and extract it with tar. Step 2, you run the config script. This is a brilliant little script that auto-detects your Linux version and dependencies and then generates a custom make file. Step 3, you execute the make command, which compiles all those raw C files into usable binaries. And finally, step 4, run make install to deploy those fresh binaries directly to your system.
But wait, I have a totally brilliant insider tip for you about step 3. Normally, running that make command compiles one file at a time, which takes around 3 minutes. But if you use the command make -j, you actually instruct the compiler to use multiple CPU cores simultaneously. By utilizing 8 cores, for example, you can slash that 3-minute build time down to an incredible 36 seconds. It saves you just enough time to realize you forgot to drink your coffee.
Now, a quick heads up about a super common post-installation headache. When you run make install, it drops your brand new Open SSL binary into the usr local/bin directory. But when you try to actually run it, it might throw an error. Why? Well, the executable is confused. It's still looking for the old pre-installed shared libraries instead of your newly built one sitting over in usr local lib. Thankfully, the fix is simple and elegant. You just create a tiny custom configuration file that points to usr local lib, and then you run the ldconfig command. This updates the master index of all shared libraries on your system, linking your new binary perfectly to its new libraries.
Finally, Section 5, Building Open SSL on Windows. Navigating the prerequisites.
Windows is a whole different ballgame. The official OpenSSL website does not provide Windows installers at all. They only give you the raw source code, so you're forced to make a choice. On one hand, you can use third-party installers from community sites like slproweb.com. This is by far the easiest method, offering simple point-and-click installers. However, if your security posture dictates that you cannot trust third-party compiled executables, your only option is to build it from source yourself, and that requires manually setting up a specialized development environment.
If you decide to take the DIY route on Windows, you absolutely must gather these 3 heavy-lifting prerequisites before you even touch the OpenSSL code. First, you need Visual Studio installed, specifically for its C compiler. Second, you must install Strawberry Perl. Yes, the Windows configuration scripts are still written in Perl. And third, you need NASM, the net-wide assembler, which is required to properly generate the final executable binaries.
Got your tools? Okay, here is the Windows build sequence, but listen closely to step 1. You cannot use a standard Windows command prompt. It will fail. You must open the specific Visual Studio developer command prompt and run it as an administrator. From there, you run Perl configure with your target architecture, like VCWin64A for 64-bit, along with your directory flags. Then, instead of the Linux make command, Windows uses nmake to compile, followed by nmake install to deploy those binaries. One last critical detail for Windows. When you're running that Perl configure script, you have to define 2 very important but easily confused directory flags. The -- OpenSSL dir flag tells the system exactly where to store the configuration files, like your openssl.cnf file. Conversely, the -- prefix flag dictates where the actual compiled executable binaries, the documentation, and the header files will be installed. Knowing the difference ensures you aren't hunting through your C drive for lost binaries later on.
And just like that, we've covered the whole shebang. You now understand the core architecture of OpenSSL, the vital relationship between libSSL and libcrypto, and exactly how to compile the source code from scratch on both Linux and Windows environments to get the latest, most secure versions possible. So, I leave you with this. How will you deploy OpenSSL to secure your next major project? Take this foundational knowledge, put it to work, and build something incredibly secure. Thanks for joining me for this explainer, and keep